the line joining which points f of a and f of a plus h. So what is that I am saying? Let me briefly again explain you. Okay, this is your interval a, this is b, this is a plus h. So your function f is already given, so f of a will be somewhere, f of a could be here, f of a could be here also, anywhere. So let's take, suppose this is your f of a, and again f of a plus h will be a point somewhere here, here or wherever. Suppose f of a plus h is this point. So this is your f of a, this is your f of a plus h. How do you define g now on this? How do you define g? What is that I am saying? That means you join these two. Okay, you join these two. I can use, don't have a red pen, but it's okay. This. So g is defined on this by this. So here is your x. So where is your gx? This is your gx. This is your gx. Right, good. Next, suppose this is your a plus 2h, and suppose your a plus 2h is here. So this is my, sorry, okay, let me overwrite. This is your f of a plus 2h. Now how do you do this? You just drop it down, right? A plus h to a plus 2h. Now take any point here. Say this is your, okay, let me call it x1, this is g of x1. Let me take this is x2, this is my g of x2. So like that. So this is how g is going. G is traveling like this. So this is how we obtain g. So obviously now we have used our understanding of linearity, and we have also used our maturity that, okay, how to make a non-continuous function continuous, make sure that it touches the end at the end point. So that is what we are doing. This is how we continue this. So I am just indicating, leaving it here. Continue this process. Right? Process of construction. We are construction of G. Continue this process of construction of G. Right? You can do this. Continue this process of construction of G. You can see that this G is linear piecewise. It is missing linearity here. So we are, that's why the term piecewise is there, because it is linear on pieces. It is not linear on the entire segment. It is linear here, then linear here, and so on. And because you are ensuring that it is touching at the end point, so it is continuous, so it is piecewise linear continuous function. Right, good. Now once we have this kind of a, so I permit me to remove this, I'm sorry for that. Okay, now things are much well behaved. Again, uniform continuity you can take care. You can take care of uniform continuity. So I'll because of uniform continuity of f. So this f of, so okay, now you can again go to the graph. I must show you how we are approximating it by linear graph. So this is what we are doing. You can see the middle graph. Middle graph is your graph f. And you can see there are small line segments which are actually very close to the graph of f. Right? Those line segments are precisely these kind of lines I have drawn here. I have tried to draw on the blackboard. These are the lines. These are the lines I have tried to draw on the blackboard. So this is really, maybe it's a little more microscopic look. But when it comes to actually sketching it, you can see that there are straight lines very close to the actual graph. So when we actually draw that, So that graph you can actually see it is lying in the tunnel. What is the tunnel? The top part is fx plus epsilon. The lower part is the graph of fx minus epsilon. Plus epsilon and minus epsilon, they are again continuous functions. So fx plus epsilon is continuous, fx minus epsilon is continuous. So you have a continuous tunnel. In that tunnel you have the graph of f, and in that graph you have actually the approximation done by the linear function. So because of the uniform continuity of f and the way you have chosen, it is check. I am leaving it to you. Check. What do you check? Fx, this is really simple, fx minus g epsilon x, this is the graph, this is how we, so I am sorry, some student must have observed. If yes, very nice, I should have written g epsilon here because I have given the notation of g epsilon, am I right? No, I have not. So better I write this g epsilon, this is g epsilon, just to emphasize that this g depends on choice of epsilon, right? So check this, this quantity is less than epsilon for all x belongs to I. I'll again go back to my graph. You can actually see my slide on the graph. You can see that the linear map, piecewise linear map which you have drawn is inside that tunnel. So that is why it has to be less than epsilon. You can actually check it analytically, that is not simple. So that actually proves this part. So what we have done is, given any continuous function on a closed interval, we are able to approximate it first by a step function. Then the deficiency was there that you said somebody would say that it is discontinuous. So we have tried to now approximate it by a continuous function, very elementary kind of continuous function, piecewise linear maps which are continuous. They are most simple functions. Now this kind of study is continued, but then I can just recall here that, as I was saying at the very beginning, that you talk of Taylor series expansion. So Taylor series converges, and when you take a Taylor series which converges, then you talk of its remainder term. Then what do you write in the remainder term? Say you are writing, for example, remainder term after nth stage. So maybe you are sometime you might be writing like this, Taylor series, and then you are saying that this minus fx is less than epsilon. So you are able to write, this is a remainder term in the Taylor series, this is a function f which you sometimes say n time differentiable, n plus one of the derivative x, and blah blah blah. So many things you assume. But then of course that Taylor series is beautiful in some sense because that you are able to do this. So this is again a kind of an approximation. You are able to approximate this. So what does this mean? This means if you are permitting an error up to epsilon, listen carefully, if you are permitting an error up to epsilon, then you can ignore Rn x from the Taylor series. That means terms after nth series in the Taylor series you can ignore. How many terms will be there? Say n minus 1 terms or n terms if you are removing from n plus 1. So first n terms, if you look at in the Taylor series, what it is just a polynomial, right? So you are saying that a polynomial can be made as close as you wish to a function f, provided you are putting so many conditions, it is differentiable so many times and so on and so forth. So that of course was there, but now we would like to see through our slides that what Carl Weierstrass did in his landmark result. I'll come back to my slides one by one. Okay. So So we were here, okay, and now this is the statement of Weierstrass approximation theorem, which tells you that if I is a closed, I hope you are able to read it properly, it be a closed and bounded interval, and f is a continuous function. So the hypothesis is same. What I have written on the blackboard, the hypothesis is same. Then for any epsilon, then for any epsilon positive, there exists a polynomial function p such that the difference is less than epsilon. Now see this polynomial we have again tried to so recall our first case was step function, then it was a piecewise linear function, now we are talking of polynomial. And if you take any polynomial, for example if you take any quadratic equation, you take then how many times you can differentiate? As many times. Of course, after second stage you will get the derivative to be 0. That doesn't really make sense, but then okay, you can differentiate it as many times as you wish. So these are all C infinity functions. Now what we do is we will try to see a proof by Bernstein using the polynomial sequences. There are some specific kind of polynomials which Bernstein has developed. There are many interesting problems that may be solved using Bernstein polynomial. They have their own interest actually, you can do that. This theorem is ideally proved for closed interval. Then you can actually try to prove it for any closed and bounded interval. First we prove it for closed unit interval, and then later on I will comment on that how we can generate a proof on a compact metric space. Yeah, what is a metric space? You know what is a metric space, wherein you have a distance. What is the distance in R? The modulus of the difference of two real numbers is the distance in R. You know that. You also know what is the distance in plane. You have 2 points, so just stretch the shortest distance, right? So that is a notion of distance. So if you have a notion of distance on any set, not necessarily a subset of R or Rn. For example, in the family of all continuous functions, you can have a distance, right? Continuous functions, you can always have a distance. That is always possible. So in a metric space, what is the state of this particular theorem? I'll try to comment on that later, right? Towards the end. We first describe Bernstein polynomial. You can see the structure of a polynomial. This book I can recommend to you. There is a book by Simmons, G.F. Simmons, which you can find in your library. That is one book, but of course this is very popular. You can go to and you can also, I would recommend here, I am not able to write here, a survey on Weierstrass approximation theorem. If some of you want to go on the net, they can find, you type this, a survey on the Weierstrass approximation theorem. There is an article in 2008, 2 years before, which gives you a very beautiful development of this, and you will also come to know so many other things. If you are interested, you can actually go into that. So let's come back to the proof. I have given you a exact statement which is on the slide for some time. I hope some of you have read it on your television screen. More specifically, what we are saying is that the sequence of Bernstein polynomial you can define which are uniformly converging to F. Uniform convergence, I'm sure most of you must be knowing. Let us see some basic properties of this thing which we want to use in our Bernstein polynomial. You all know what is binomial theorem, must have used several times, and for any integer you can actually prove what I have written. This is very simple. You can actually prove this. Many of you must have proved that, where I am writing what is R epsilon x. This is combination of n objects taking k at a time. So this is just a kind of a polynomial again. So I am just indicating this. This is very simple to be proved. Now once you prove that, let's look at a proof of the theorem. There is a very celebrated theorem of Heine-Borel which says that what are compact sets in Rn, for example. What is Heine-Borel theorem? Heine-Borel theorem tells you that the compact sets in the Euclidean space are precisely closed and bounded subset, right? The duster in my hand is a closed and bounded set, so it's compact, right? Me as a individual is compact. The television you are looking at is compact. This is a closed and bounded set. The glass which you might be holding drinking water is compact. So these are all compact sets which you know that this is possible. So when you talk of these compact sets, you can actually take your functions to be continuous and bounded. Therefore you can find out a Bernstein polynomial for every integer n greater than 0. You can find this. These are some simple calculations which I have made, fx minus this. So if I keep on reading it, it won't make much sense here to read out these calculations. I have though listed here just to make sure that you feel confident that you can do it. It is playing with just simply binomial theorem and some of its utilities. You can actually do that and you can find out these calculations. These are not difficult to be done. So I am just skipping this. Now here in item number 3 you can actually see that, okay, let me go back. to 1, you know. So 1 is again uniform continuity. See, this is a brute force, you know. We are actually using this uniform continuity. Since the beginning we are using it. So because of this uniform continuity, you can talk of 3. You can talk of 3, that is possible. It's simply possible. And now you can make some elaborate. Suppose mod of x minus k by n is greater than or equal to delta, then how to handle that situation, that also we have done. There will be 2 situations. One, when this is less than delta, right, and another one when this is greater than or equal to delta. Both the situations can be handled, and when you are able to handle both these situations, there cannot be a possibility of the third situation. So you are able to handle it on the entire interval, right. So therefore you are able to approximate by the Bernstein polynomial. So this is some simple calculations which are done. I am sure many of you will be able to do. I am just skipping it. These are some calculations which are made just to make you feel comfortable. You can do it. Just elementary arithmetic and some kind of approximations when we are doing. So this is just equal to. You can always do this, right? So I'm really pushing it out of this place. So you can see that the construction which we have made. So f mod of fx minus b mf fx, we can actually make it less than a specified constant, which will help for us. So both the situation, right, both the situation, when you have this is less than delta, mod of x minus k by n less than delta and greater than or equal to delta, can be handled separately, and therefore you can actually prove this. Now actually, so this is how the proof goes here. So Bernstein polynomial is a specific type of polynomials created, and then you can approximate it by using binomial theorems and some small results which I have illustrated in the beginning. Now any closed interval can be put in bijection with the closed unit interval. So if I have 0, 1, and if I have any closed interval, then I can put it in bijection. Say this is always possible. So imagine your closed interval on unit closed interval on the x-axis and any interval AB. So send 0 to A and B to 1 to B, and then sketch a line, write the equation of that line. That equation of the line will give you the bijective map.